Welcome to our next video in the Chapter 3 journey of the atom. Today we will be looking at how to express and determine the amount of subatomic particles in an atom. Let's begin with looking at what makes an atom unique from other atoms. We briefly mentioned in the previous video that if we change the number of protons, we change the identity of the atom. Since the number of protons is important to the identity of the atom, we will call it the atomic number. This number is different from the mass number. The mass number is the total number of protons and neutrons in the nucleus of the atom. You'll notice we don't care about the number of electrons when describing the atom. This is because they basically have no mass and move easily between atoms when compounds form. But we will save that discussion for a next chapter. Now, you'll remember one of the changes to the atomic theory was the idea that one atom can have different masses. In order for it to be the same atom, the number of protons, however, cannot change. That means the other particle that contributes to the mass of the atom must change, and that particle is the neutron. When atoms contain different number of neutrons, but the same number of protons, we call them isotopes. Because there are so many different isotopes for a certain atom, we need a way to show which particular isotope we are referring to, and there are two ways we can approach this. The first is by hyphen notation. In hyphen notation, we take the element name, which is based on the atomic number or the number of protons, and follow it with a hyphen, then the mass number. So for example, we could have where carbon is the element name and 13 is the mass number. This is then a specific isotope of carbon. The second way is through the nuclear symbol. This time, instead of the element name, we are going to use its symbol. Then, in front of the symbol, we list the mass number on top, and below it, the atomic number. So if we were to use the same isotope as above, it would look like this. C for the symbol of carbon. On top is going to be our mass number, which is 13. And then we would just need to look up what the atomic number is of carbon, and that is 6. So that is the nuclear symbol for carbon 13. If we know the number of subatomic particles, we now can express what isotope we're referring to. But what if we only have the isotope information and want to know how many of each subatomic particle we have? Well, that's easy. It just takes some simple math and maybe a periodic table. If we want to know the number of protons, we simply find the atomic number. In hyphen notation, we would need to look up the element on the periodic table and look for a small whole number. In your book, it is the number on top of the symbol in the periodic table. If we had the nuclear symbol, it is the number on bottom, so we would just have to write it down. To find the number of neutrons, we must take the mass number, which is given in both hyphen notation and nuclear symbol, and subtract from it the atomic number, or the number of protons. Finally, to find the number of electrons, we look at the atomic number. That is because the atom is neutral, so we need the same number of electrons to balance out the charge of the proton. This does not hold true all the time, and we will discuss why and how, guess what, in a later chapter. So let's practice. If we want to know how many protons, neutrons, and electrons there are in an atom of chlorine-37, well, you can see we have hyphen notation there. So what we'll first have to do is look up chlorine on our periodic table. Have you found it yet? Still looking? Well, chlorine, if you haven't found it, is atomic number 17. Chlorine symbol, for all of you looking, is Cl. So chlorine has an atomic number of 17. So that means it has, or its protons equal 17. Because we know number of protons and number of electrons have to be equal, we can skip ahead to electrons and say our electrons also equal 17. Now to find our neutrons. Well, we know that 37 is our mass number. And 37 means we have protons plus our neutrons that equal 37. So if we already have or know we have 17 protons, we can take 37 minus 17, or our mass number, minus our atomic number, and that gives us 20, or 20 neutrons. So again, using our periodic table, having to look up a little bit, and doing some simple math. So now we want to write the nuclear symbol for copper-64. So remember, the nuclear symbol uses the symbol for the element. So we need to look up copper on the periodic table. Keep looking. Did you find it? If you haven't yet, copper's symbol is Cu. Now, don't lose it, because you also need to look up its atomic number. So again, this is the small number above the symbol, and that is 29. Now, when we're writing the nuclear symbol, that atomic number goes before it on the bottom. So we're going to put 29 on the bottom. The rest of it is easy, because then we just need to copy the mass number and put it on top. So 64 over 29 Cu for the nuclear symbol. Nuclear symbol is also nice and easy then if we wanted to determine the number of neutrons. It doesn't ask us to, but if we wanted to, basically it's a math problem. So 64 minus 29 would give us our number of neutrons. Write the hyphen notation then for the element that contains 15 electrons and 15 neutrons. Well, if we look at the previous screen, it doesn't tell us anything about electrons except that our number of electrons equals our number of protons. And our number of protons is our atomic number. And why do we need the atomic number? Because we need to figure out what is the element. So we're going to look it up again on our periodic table. So we're going to look for a small number 15. Have you located it? Okay, 15, hopefully you have found, is phosphorus. So in hyphen notation, we write out the whole name, not just a symbol. So phosphorus, hyphen, because it's hyphen notation, and then we need the mass number. So remember, the mass number is our number of protons plus our number of neutrons. So if we take 15 plus 15, we get 30. So this would be phosphorus 30. Now, if we take a closer look at the elements in our periodic table, you'll notice that there is a number below the symbol. This is the atomic mass. The numbers, however, are not whole numbers, which would lead us to think that we are not working with whole protons or whole neutrons. But in fact, we are. That 0.45 doesn't mean we had point something of a proton or point something of a neutron. That comes from an average. Well, how we get averages? Well, first we have to look at where do these original numbers come from. Well, basically we looked at everything relative to carbon-12. This is the most abundant isotope, easy to work with carbon. Carbon's in almost everything. So that's why we use carbon-12. When we related these to carbon-12, we were able to come up with an atomic mass unit, the AMU. You saw me use that when we talked about the mass of the proton and the mass of the neutron as being 1 AMU. Well, an atomic mass unit equals 1/12 the mass of carbon-12. So basically, if you added your protons and you added your neutrons, we came up with 12. Divide that and we get 1. Our average atomic mass. This is the average of atomic masses of all isotopes of that element. So when we look at carbon, for example, we look at all of the abundant isotopes. There's carbon 12, carbon 13, carbon 14, probably carbon 11, and so forth. So we're going to take all of those and find an average. Well, we can't just easily just add them up and divide by 3 or divide by 4. We also have to take into account how abundant is that isotope. To find this, it looks like a long, drawn-out math problem, but it's really not. We take the mass number, so the mass of the isotope. So this is the mass number of the isotope. And we're going to multiply it by the relative abundance of the isotope. So this is one isotope, let's say, of carbon. Then we add it to another isotope of carbon. So the mass of that isotope times the relative abundance of that isotope, and so forth until we've used all of them. So the relative abundance is basically just found from how often does that occur in all of the isotopes, and we give it a percentage. So it's the percentage of all isotopes of a particular element. So this all sounds really confusing. So let's work with one. So if we found a new element, and we looked and we got a bunch of different isotopes of that element, compared how many we had to the total, and we came up with percents. So we want to know what is the mass of this new element. It is 22% of element 515, 33% of the element 514, 2% of element 516, and 43% of element 513. We know these are isotopes because we got hyphen notation. So we've got the hyphen to show us we have hyphen notation. So how do we find the mass? Well, first is we got to look at percents. Whenever you work with percents, remember we move the decimal place 2 back because we want to get rid of the percent. To get a percent, we multiply by 100. So to get rid of the percent sign, we're going to divide by 100. So we're going to take this first isotope, and we are going to say we have 0.22 times the mass number, 515. So the mass times the relative abundance. I did it backwards from the screen. This is just what I do when I'm determining, but it doesn't matter because it's multiplication, and multiplication can be done in either direction. And then we're going to add it to the next isotope. So the next isotope is element 514. So we're going to take 0.33 times 514. Then we have 2% of element 516. Now be careful with 2. We can't put 0.2. If we move it back 2, because we divided by 100, remember this is then 0.02 times 516. And finally, we use our fourth isotope, which is element 513, and we take 0.43 times 513. We plug this all into our calculator, and our answer should give us an average atomic mass, which equals 513.83 AMU. So the concept seems kind of difficult. We're relating it to carbon-12. We're finding out what this atomic mass unit is. And then we're taking all the different isotopes and adding them all together. But somebody usually does that math for us. We just need to know the percents, know the isotope we're talking about, and then we can add them up and find our average atomic mass.